Good morning, students. This is Syed Fahad Anwar. I am the instructor of your course on Fluid Mechanics 2, that is EMEC 3310. I will be taking you through this whole semester on the from this in the course of time on the Fluid Mechanics 2, that is EMEC 3310. So today's video lecture is about the contents that we will do in this course, or which we are going to discuss with this course. So today we are going to just introduce this first lecture is about the introduction to this to the course of Fluid Mechanics 2, and how does it talks, or how does it connects with the fluid mechanics in general, or that means the applied applications of fluid mechanics, and the connection with the Fluid Mechanics 1 course, which you have already studied, that is EMEC 2310. So let me first introduce our course, that what are the different course objectives. So as you know that in all the courses we always have certain objectives which you want to transfer to the students. So in this course, the first objective is that we should be able to model or express viscous fluid flow using physical principles. So as you all know that and you have studied some of these physical principles in your mechanics and fluid mechanics, in your mechanics and fluid mechanics first course, and these principles are nothing but the conservation of mass, the conservation of momentum, and the conservation of energy. So these physical principles, when they are applied to the fluid flow problems, these are basically the apply to physical problems. So we will be, the first objective is that how to apply these physical concepts, these physical principles to a fluid flow problem. And in this, basically what we are trying to do is that we will relate this to the second objective, which is that we have to we will try to make you understand the behavior of viscous fluid flow by examining certain flow problems. So what do you mean by this? Is that we will then try to as you know that once the physical principles are written, they will give you certain governing equations, and these governing equations will be then solved with the help of analytical tools to give the fluid mechanics solutions, or the exact solutions, which we call them by exact solution, to well-known problems like pipe flow, like flow in a channel. What should be the flow in a channel? What is the flow in a pipe? And from that, we will try to help you or develop the mathematical skills and skills to solve this. Now, as you know that the governing physical principles are slightly complicated in nature. That what do I mean by complicated in nature? Is that the governing principles are mathematically complicated. That means they are sometimes nonlinear in nature. So we need to apply relevant mathematical skills, or we will some mathematical tricks to solve these fluid flow problems. So these tricks or mathematical skills, I will not call them as the tricks, but mathematical skills, we will try to imbibe you. What do you mean by imbibe? Is we will show you how to use these tricks or skills, or we will develop these skills by demonstrating to you in solving these flow problems. Now, and then we will we will try to discuss with you some important phenomena which have been done. So once the this whole is divided into two parts. One is basically the development of the main physical concepts or the mathematical and physical concepts of the fluid flow, and then we will try to apply to more application based flows like the evolution of boundary layer, and we will also give you the taste of turbulence and how we uh, tackle turbulence, and how you are going to solve some of the part of the turbulence, basic understanding. Now let me take you to the next slide, which is what is the role of fluid mechanics. What do I mean by the role of fluid mechanics is that okay, where, in which areas, or why fluid mechanics, studying of fluid mechanics is important. So as you see that I have given you a lot of fluid flow examples, and these examples, as you can see, the first category of application is the power generation, land, air, sea transport systems or vehicles, earth fixed structures, heat transfer or heat removal, transport of fluid properties, and etc. Now, as you can see that I have given you examples of I have given you pictures of fluid flow, like a person who is in a who is working on a computer. So computer is generating heat, and the person itself is generating heat, and you have to design a system where a well ventilated system, so and the cooling system, so you need to remove the heat from those systems. So how you are going to do that now, and then then I have given you examples of a pressure variation on plane and on an aeroplane, and you can see that the red zones are places where you will get the maximum amount of pressure. And I've also given you another example of a pressure variation on a on a car, or specifically a sedan. So you can see that how the fluid flow is evolving on a sedan. So nowadays, the example of these are done. There is for designing the external aerodynamics of a missile, or external shape of a missile, or for example of a car, or so you need to know the pressure variation on the whole of the on the surface of the aerofoil, or the missile or the car. So there are facilities, like one of the facilities I would like to mention is a National Wind Tunnel. So in a National Wind Tunnel, which is located at IIT Kanpur, you can put a whole truck on that on the test section of the wind tunnel, and you can measure the force which the flow will apply on the fluid on the structure. Then there is another example of sports like swimming, where people have used by fluid mechanics to study the effects of how backstroke or other strokes are used, or how these strokes can be changed to augment their swimming skills. If I talk of the swing of the cricket ball, that is purely fluid mechanics. So how the bending of the ball. So the swing of the cricket ball is that the so the deviation which a bowler can impart due to the air, due to its flow in air, the ball's flow in air. So it's very important how you hold the seam and all those things. So these explanations can be given by the fluid mechanics of how exactly the ball is bending. So these are the places you can use the you are going people are going to are using it in technology. Now the in the environmental or geoscience, people, you can see there are examples of atmospheric or oceanic flows or weather prediction, hurricanes, pollution dispersion, and convection in the core. So I have given you 4 examples. If you will see in the bottom second picture from the bottom from the bottom, it is basically of a of a sand plume over there. Then there is a picture of a volcano, and then there is a picture of taken by NASA of a vortex shedding pattern from a galaxy. Then there is a pollution dispersion from a chimney. So these are all very much related to the fluid mechanics. So you can see that from the trans technology to geophysics to biological system, the respiration which we all know is basically pure fluid mechanics. The circulation. So if you can see that on the right top right corner, there is an artery and there is a coronary artery, and from that and in that there are a lot of fluid is flowing. So this coronary artery, and this is a pressure calculation by CFD. We are calculating the pressure, and this is the picture from there. So this is a process of fluid mechanics. Then there is biomedical engineering. You have an eye, the corona, the arterial pressures, the corona, the pressure in the eye. So it's all fluid flow phenomena. Then the pressure in the you might have heard of the brain stroke. So there are cerebral fluids which are there in your brain, and then due to some blood pressures, it might burst. So the fluid and the cerebral fluid and the blood mixes, and then it causes havoc in the body. Then there is a chance of the insect aerodynamics. So you can see in the bottom picture is a vortex shedding from an insect. How this changes it. Then we have lubricating systems, flow around cooling towers. So you can see that fluid mechanics, the role of fluid mechanics is very important from how you see and speak and you breathe to the evolution of stars and galaxies and the astrophysical jets. So you can see that it's a very, very vast and a very important field of study. Now I will try to relate this course or fluid mechanics to the mechanics course which you have studied in the first year. You can see that mechanics is just a classical mechanics where you have particle, and then you have certain particle, and on that particle there is force applied. Now if you break this into two, you can break this into two parts. The classical mechanics can be break down into two parts. One is the mechanics of rigid body. So mechanics means force and its effect. Dynamics is basically force and its effects. Statics is the force and its effects into motion, and statics is the force effects of force on the body, and together this is called mechanics. So rigid body mechanics is the mechanics of bodies which are not going to deform, and then there are classical mechanics can be broken down into two parts. One is rigid body mechanics, and the other is the mechanics of deformable bodies. That means those bodies which can change its shape. So that is the main difference. Then this mechanics of deformable bodies can be then divided into two parts. One is the molecular mechanics. That is, if the particle is very, very small, and that is on a molecular level, then either you use molecular mechanics or statistical mechanics. You consider the variation of multiple particle systems into account, or you take the single molecule and then apply the fluid mechanics or physical system laws. The other particle is this, the other part is the continuum mechanics. So so the continuum mechanics, which you have already, continuum assumption, which you have already studied in fluid mechanics 1 course, and that is basically the as we will talk about that later in the course. So you have a continuum mechanics where you have a large number of particles, and these particles are functions, or these particles are basically these properties are the properties of the particles are functions of space and time, continuous functions of space and time. So if you break down this continuum mechanics into two parts, one will be the solid mechanics, or the mechanics of finite deformation, where you have a solid, and and any amount, only a given amount of external force can deform it. But if this given amount of external force is the smallest shear force, then it comes under the fluid mechanics bracket, which is basically the field of study. That is there, okay. And let me so you can see how is the fluid defined. Fluid can be defined as a substance which continuously deforms itself by the application of smallest shear force. That is how the fluid goes. So now I'm going to relate with the fluid mechanics 1, which you have already studied in the last course, which will be now. I will just review it. So the first point is the first thing which comes to a part is what is a fluid. So what is the notion of a fluid particle? We need to answer that. So what is the notion of a fluid particle? The notion of a fluid particle comes from the continuum or the macroscopic viewpoint. So whatever you see right now, if you will see, you do not see that the air, as you know that the air is full of different type of particles, but if you see that, you do not feel any change in and you do not see any particle. So it's a macroscopic viewpoint. So you are viewing from outside, and you as a large bunch of particles, air particles or any fluid particles, any substance, large bunch of substance of particles as a fluid. So you can assume that if any space is there, it is continuous in nature, and the properties are continuous in nature. This will be considered as the fluid viewpoint. So if you want to define a fluid, as I've already said, that a fluid is defined as a substance which can continuously deform itself under the application of a slightest shear force. So the words which are important is the continuous deformation and the slightest shear force. So these two words. So if it doesn't deforms continuously, it is not a fluid. If it can withstand certain amount of shear force, then also it is not a fluid. So if once you have a particle that is a fluid particle, then on a fluid particle there must be some forces. The mechanics is defined by some forces, and these forces are of two types. One is surface forces and the other is the body forces. So you have already studied the state of stress at a point and the force intensity at a point. So how you can write down surface force, and how you write down the body force. So this you have already studied. Now surface forces are shear forces or pressure forces, while body forces, as you already know that body forces are the forces like external forces like gravity, electricity, electric field, and all those things. The next point which we need to consider is, which we have already studied, it is the fluid statics, where you might have studied the notion of pressure. It's always compressive in nature, the hydrostatic equation and its related applications. So you have studied the hydrostatic equation, like that is minus grad P is equal to my rho g minus A. So rho times of g minus A. So gravity minus the acceleration. So this explains, you can with the help of this, you can explain the why the meniscus of a fluid, the shape of the meniscus of a fluid which is exposed to the pressure. If a surface is accelerating, what is will be the shape? How does pressure will be defined over there? Then the forces on a dam. You can use that manometric equation. You can use the manometric. You can solve the manometer pressure in the manometer. Kind of things, and then you have you apply for this for the buoyancy related or the stability of the fluid. The second part of this which you have studied is the kinematics, and in kinematics you must have studied the Eulerian and the Lagrangian viewpoint. So I will just briefly explain what are these. The Eulerian viewpoint, as you already know, is the is the totalitarian viewpoint. So first I will explain the Lagrangian viewpoint. So in Lagrangian viewpoint, you consider one fluid particle as your system, and the variation of this fluid particle or the interaction of this fluid particle with the force is the object of study, and how this changes is basically the point. Now, in the Eulerian viewpoint, you do not consider a single particle, but the whole bunch of systems, bunch of particle as a point, and you do not sit on the fluid particle and then see the experience this you experience this on a bunch of fluid particles. That is the Eulerian viewpoint. Now, you might have also studied the flow visualization, that is streamline, streak line, path lines, and material lines. So these are the tools of how we can visualize the flow. That means like streamlines are defined are the lines, are the imaginary lines which are the tangent to that line gives you the velocity vector. The streak lines or path lines. First, I will explain the path lines. The path lines are the lines which the lines which are pass through one point. So suppose you have a you put a paper in a fluid flow, and you try to see how it goes, like when you have a rainy season, people put a boat on the boat in this, and you see that how the boat travels. So that will be the path line of the particle which are attached. Those will be the path followed will be the path lines of the particles attached on the boat. And the streak lines, if you take a picture of this particle, so it is basically, there are few particles like particle A, B, C, D, and all pass through point x naught. So if they all are passing through point x naught, and if you take a locus of these paths, these lines, these locus of the locus, if you take a picture or basically the locus of these points where they are, and you join them, then that line would be called as the streak line. Material lines are the most simple things. They are just the two lines, they're just a line in a fluid flow. That is the most easier thing. Now, the important thing is the material derivative, which you have already studied in the fluid flow problems, which has a if you have a capital D by dt. So that is basically the fluid flow material derivative, and which has a one part is the local and one part is the space variation. So now if you apply this on a velocity, it gives you capital dV by dt. It gives you acceleration of the fluid particle. Now one part will give you the local acceleration, that is del v by del t, and the other part, say u del v by del x plus v del u by del y, will give you the convective acceleration or the acceleration due to space variation. Now you also have studied the dynamics of inviscid flow, like Euler and Bernoulli in your last course, and you have applied these principles to the finite system, that is the control volume approach, by using the Reynolds transport equation. This is very important. And from the Reynolds transport equation, and then you apply the Bernoulli equation to the viscous pipe flow and calculations of the energy loss, how the energy is lost in transition in a fluid flow. So these things you have already studied, and I will recommend that you should go through these things and revise those things in your home, and we will try to help you out wherever we will feel that we need to do that in next course. But in this course, which is extension of the fluid mechanics 1, we have divided this into 3 modules. So the first module is the mathematical model of is the dynamics of viscous flows. The first is the kinematics. That first part we will be dealing with in module 1 lecture 1. We will discuss with the kinematics of the strain rate at a point, the vorticity, what do you mean by vorticity, what is the velocity gradient system or tensor. Then we will try to develop the governing equations. Then we will also show you the dimensionless formulation and the dynamical similarity. Then we will solve some exact solutions. Now I will just elaborate a few points over here now. Like kinematics. So kinematics, the first part of the kinematics is the strain rates at a point. Now if you do not know the strain rates at a point, so the governing equation on a particle is like force is equal to mass into acceleration. Now the force you can write down is mass into acceleration, and the force is due to the interaction of the fluid particle surroundings or surroundings with the particle surrounding, solids surrounding with the fluid. So therefore there will be certain interactions. Okay. Now these governing equations are like stress balance equation or momentum equations, or the will require the strain rates. So the most basic thing in a fluid system is the strain rate. So how you are going to write down the strain rates? The strain rates can be divided into 2 parts: the longitudinal strain rates and the shear strain rates. And how to relate these strain rates with vorticity, that we will be telling you. And the final thing is the velocity gradient system. We will use these strain rates to develop the governing equations, that is the mass conservation equation and the momentum conservation. So generally in this course of fluid mechanics 2, you will only use mass conservation equation and the momentum conservation equation. And these mass and momentum conservation equations, there's in the heat transfer course, which you have already started to study, they will be telling you about the energy equation also. So but we as a system, we will only discuss with the laws of mass conservation and the momentum conservation. So from the stress balance of on a particle to the strain rate, so we will show you how the differential equation comes out. and these will be similar to something similar to the Reynolds transport equation, which you have get from the momentum equation. So momentum balance equation from the Reynolds transport equation in the fluid mechanics 1 course to this part. Now it will the Bernoulli equation of it will also look like Euler equation, except that in Euler equation, what's one of the most important thing is that it doesn't takes into account the viscous part. That is, it is only valid for inviscid flows. So that is why Bernoulli equation cannot be applied to the inviscid flows. Now we will add to this knowledge, and we will show you how the viscous forces should be modeled, and we will come out with a complete equation of which is going to model any incompressible fluid flow problem, incompressible fluid flow problem. The third part of this is the dimensionless formulation. So how? So you have already studied dimensionless formulation in your last course, and we will show you how to do the dimensionless formulation for an equation and what is the use of it, how it can be the knowledge of the dimensionless formulation and its value of the parameters can be used to derive some very important approximations and some very important logics, and give you the very good reduction in equations. The dynamical similarity, again we will show you. So now if you do experiment, you cannot have a airplane on a wind tunnel, in a wind tunnel, and do the calculation. You measure the force and drag which is it's going to calculate, because obviously the airplane is very big, it cannot be fit into any wind tunnel. So if you want to have a prototype which is smaller in size, then what are the ways, or how do you have a lab scale model and a prototype, how do they match each other? So that is the second part. Then we will use these above formulations and examples to solve some exact solutions. And that is these are canonical flows, which like pipe flow, flow between two concentric cylinders, like flow in a channel, flow started by between two plates. One plate is moving, one plate is fixed, and all these stuff. Then we will use the second, then we will come on to the second module, which is the application oriented module. You have you apply boundary layer theory. You develop from the Navier-Stokes equation, which is the governing equation for the fluid flow. You develop a reduced order equation by using dimensionless formulation, and these reduced order equation are called boundary layer theory. These are very important equations, and they help the first time to evolve the new age aeroplanes. So these were the equations which first time gave you the correct prediction of lift and drag, and so it's very important to understand this. It also help you understand the boundary layer theory. It also help you understand the flow separation. So therefore, if you can understand the flow separation, then you can also understand its control methods. Now, these two are the above first part of the boundary equation and its solution is normally in differential approach, but there is another integral approach also. So we will discuss that approach also, which gives you a faster calculation of these concepts. But that is also applied to only boundary layer theory. So the next module is the turbulent flow module. In this module, we will introduce you to the different characteristics of turbulent flow, and why there is a large amount of length scales and time scales involved in a turbulent flow. So as you know that you might know that on a flat plate, which is 0.1 meters long, and air is flowing on a flat plate with a velocity of 2 meters per second, it will give you a smallest length scale of around 1 mm sorry 0.01 mm, and the largest length scale will be of 40 mm. So you can see that such large amount of length scales are involved in this flow. So in this course we will discuss you what are the what are the different scales, and can you relate it to the Reynolds number of the scales, Reynolds number of the flow to these times length and time scales. And we will also discuss you why this statistical approach was needed to solve the turbulent flow, and what is the effect of the statistical use of statistical approach, and how does the mean flow equations come into the play. And these mean flow equations are called Reynolds average Navier-Stokes equations, and this creates this averaging procedure creates certain additional terms which needs to be modeled. So these are called as a closure problem. This is called as a closure problem because you do not have an equation directly available for that. So this all will be taught in this fluid mechanics 2 course, and we will and the methodology of teaching will require some supplementary text and study materials. So as far as our understanding concerns, these lecture notes are probably will be these lecture notes, that is videos which we are going to upload, plus the PDFs of the lecture notes will be detailed PDFs of the lecture notes will be quite comprehensive in itself, and they are very well developed by us, and it shows our understanding of the fluid problem. Though this fluid mechanics course is quite general in nature, and you can find a lot of books in where you can read supplementary materials, but we will like you to read these 3 books, which is Viscous Fluid Flow by F.M. White, Viscous Fluid Mechanics by Piyush Kundu and Cohen, Incompressible Flow by Ronald L. Panton. And if some of you are not native English language, not comfortable with the English language of foreign authors, they may want to have a look at certain good books of Indian authors. So then this book by Advanced Fluid Mechanics by Somin Bishwas, Professor S.K. Som of IT, probably Kharagpur or Guwahati, and Professor Bishwas is from IIT Kanpur, and they have written a very good book on advanced fluid mechanics by Nerosa publication. I believe there is an NPTEL course by these people also on on fluid mechanics. So if you want, you can have a look at it. There is also the algebra, and we will be also requiring you to download from my web page these 2 sheets, and I will also post this in the group, the algebra and calculus of vectors and tensors, and some important results and theorems of the vector calculus. So these 2 mathematical aid sheets will be allowed to use in your exams and mid semesters. These you may require these sheets for help, because we do not want you to remember those equations, we want you to understand those equations. So for remembering part, you can always have a look at these vector tensors and theorems where these equations will be given, but to solve them needs understanding. And this course is again, if whatever we know right now, it is like something like 70-30 kind of a thing, where 70 would be for the continuous evaluation part, where there is a mid-sem, will be assignments, and the 30 will be the final exam part. So these assignments we will be giving you weekly basis, or basically on once we have certain text covered, certain part of the course covered, we will give you, but it will not be 1 or 2 assignments which I used to give in the other classes, because this is online. So we need you to be more attentive in this course, because I'm not going to teach you through every video lecturing. But we will have interactions. Some courses some part of the course which I think are important, I will teach you online, and others I may not teach online, but I will give you video lectures, or this kind of a presentation with voiceovers. So because sometimes some of you are not there, not have good speeds and all those things, so that you can watch it on your own free time. So I would like to conclude this lecture now, or close this lecture now. Thanks.